Hi everyone. In today's video, I will be showing you the Precal explanation behind why the angle side-side case works the way it does. So first, let's make sure we understand what the angle side-side case is. The angle side-side case is when you have a triangle, an oblique triangle in particular. We have angles ABC, and we have sides little a, little b, and little c. And you are given enough information for, in this order, an angle and two sides. So let's say we are given angle A and side C and side A. Now this is enough information to use the law of sines, but this creates an ambiguity, is what we like to call it, meaning that the angle C could have up to two different measurements. So I like to call this angle a flexible angle. And basically we actually split it up into two cases. So the first case is we have a triangle that looks like the one I already drew. So we have ABC, and we are given the same information. And this is the case 1. Angle C is acute, which we're kind of making that assumption in this drawing already. And then the second case, I'm going to draw quite a bit differently. And then ideally, obviously you may not believe how it's drawn, but this given information is exactly the same, but the other cases, you see I drastically changed the size of angle C. Case 2 here, angle C is obtuse. So that is what, in essence, the ASS case does to a triangle. When we start with a triangle with this information, there are actually up to two possible triangles we can make out of it. Now we're going to discuss why this happens and how we can tell the difference. So, the why, the big question. Using Precal. Let's go back and talk about some basic unit circle stuff. So let's say we have the problem sine of theta is equal to 1/2. So if we solve that using our calculator, it'll look something like this. So we have sine of theta equals 1/2. And then first we'll do a little solving on paper. To get the theta by itself, we need to take inverse sine of both sides. So that means theta equals inverse sine of 1/2. And then we can use our calculator to get our answer here. And we get 30. So theta is equal to 30. So that means that our angle here is 30 degrees. Now let's solve that again using the unit circle. So once again, the same problem. We have sine of theta equals 1/2. Now this time we don't use the calculator, we just look at the unit circle and we find exactly where our theta is equal to 1/2, where its sine value is 1/2. So if I pull up my unit circle here, so we look in the first quadrant and we see that sine is 1/2 at 30 degrees. That is no surprise, we've already discovered that. Theta is 1/2, theta is 30 degrees. But we take a second look at the circle because reminder, the majority of the time when we're finding theta on the circle, we can usually get up to 2 angles for theta, not just one. Sometimes it is just one, but most cases it's actually 2. So if we look, in the second quadrant, there is another angle where sine is 1/2, and that's at 150. So 150 degrees is another option. So what we can conclude here is that the angle is 30 degrees or 150 degrees. Now this is a case where both answers would just be accepted as the correct answer, but we don't know which one we're going for this problem. So those are both our answers, hence we'd write them as a comma-separated list. Now the reason that it doesn't show up in our calculator is actually quite simple. So we are using the inverse sine function. So why does this happen? Or why does this not show up on the calculator? We are using the inverse sine function to solve for our angles. And for the inverse sine function, its range is -90 to +90. And when we are using the inverse sine and we're getting our answer, that's our angle. So theta is equal to inverse sine of whatever our number is. I'll just write it in a very general term here. And this is our angle measure. Now, since the inverse sine function can't give you a number greater than 90, because 90 is the limit, inverse sine cannot produce obtuse angles. So I'll write that down. Since inverse sine can't give a number larger than 90 degrees, and we know 90 degrees is a right angle, it can't give us an obtuse angle. And just a quick reminder, in case it hasn't fully clicked yet, the range, of course, are all the outputs. So, this sentence right here that I just wrote, this is the big why this whole phenomenon I've just described to you happens. Since inverse sine can't give us a larger than 90, it can't give us an obtuse angle. So when we are using law of sines to solve this triangle, this case number 2 will never show up with the calculator. But it could still be out there, we don't know, that's the problem. So we have to go looking for it, is what's happening. So let me finally demonstrate this with a real example. So we have our example, actual numbers to work with. Let's say we have our triangle ABC. And angle B is 61 degrees. Side A has a length of 35. And then side B here has a length of 32. And then let's say that the directions are just solve the triangle. Now I'm not going to fully solve it. I'm going to go as far as I need to demonstrate the point. Or actually, I will go ahead and fully solve it because I know some people might benefit, but feel free to stop the video once you feel like you've gotten what you needed out of it. So first off, we look and we classify the triangle. We have angle, side, side. This is indeed the ASS case, the case we have to be careful of. So naturally, we use the law of sines to start solving. We're given the B's and then part of the A pairing. So our natural direction to go from here is to find angle A. So we use sine of A over A, and then we're given the B's, sine of B over B, and then I'm going to fill that information in with what's in our triangle. Sine of A over little a is 35 equals sine of B is 61 over little b is 32. And then from here we cross multiply. Cross multiplying, we end up with, I'm going to skip just a tad bit of the work. Sine of A equals, this fraction on the right will turn out to be 35 sine of 61 over 32. And then to find A, that's when we take that inverse sine on both sides. A is inverse sine of that fraction, 35 sine of 61 over 32. And then, of course, we need our calculator to get the measurement for A. And A rounds to be 73 point, we'll go out to the tens place, 1 degree. So 73.1 degree for A. I'm going to come back and fill that in my triangle. 73.1 degrees. Now, if we weren't being careful and didn't notice that this is the ASS case, we would just continue on, find angle C and side C and be done with the problem. However, there is a possibility for a second triangle. Notice here, and this is kind of the big turning point of the problem. I'll put it in here. Angle A is bigger than angle B. Here's another big problem as to why we have to do this. We don't know the size of C. If C is the largest angle in the triangle, then we can just go ahead, finish the problem, and be done with it. We don't know for a fact that that is the case. And the problem is, if we just push on and assume that's the case, we can land ourselves in some big trouble. So, this is the only relationship we know. A is bigger than B. That's it. So, that leaves two options. Option 1, angle A is acute. Or angle A is obtuse. Since we know that A is bigger than the given angle, it has options. It could be acute or it could be obtuse. Here's the problem. We don't know which one it is, and we won't know. That's why we draw out both triangles and we set up both scenarios, so we're basically covered. Reminder, what I said earlier. Inverse sine can't give a number larger than 90. So it can't give us an obtuse angle. So that means that we were given this number because that was the only number that the calculator can give us. Could this be our answer? Yes, but again, we don't know. We will never be able to figure out which triangle it is. We just know that there are two possible triangles that could be the answer. So we draw both of them. What we do know is that there is another angle out there that can make this triangle work, and it's an obtuse angle, and we have to go find it because this calculator will never give us that measurement. So we have to use a relationship between these two angles to get that second triangle. And I'm going to do that on a separate piece of paper. So let's draw the second triangle. So our second triangle is going to be the obtuse case. So I'm going to intentionally draw it to look obtuse. I just think it makes the problem a bit more believable if I draw the triangle that I'm going to have the measurements for. So it's still ABC. B is still 61 degrees. Side A is still 35. Side little b is 32. And then I'm going to add ones here so we can easily differentiate between the two triangles. So this is the second possible triangle. So the same given information, but we're now considering a different A value. We found the scenario where A is acute, and since it's bigger than B, and we don't know how it compares to C, that means A could still be the biggest angle in the triangle. So we have to explore what that would look like. So to do that, what's convenient is that when you add these two angles together, that gives you 180 degrees. So to find A1, it's actually quite simple. It's just 180 minus A, which is 73.1 degrees. And that is A. And that is going to give us 106.9 degrees. So A1 is 106.9 degrees. So again, we are exploring both options. Option 1, A is acute. Option B, A is obtuse. You can do this every single time if you're not sure. Now, if you notice that A is smaller than B, let's say we had the opposite scenario, you wouldn't have to go into all of this because this wouldn't make a triangle. You could still do it, but you're going to do some extra work just to find out that it's going to fail. So that's completely up to you. If you want to be safe and do it just in case, go right ahead. But this is the problem where it does work out. So now we can, in either order, finish solving both triangles. That is completely up to you. So I'm going to finish the second triangle since I've already started it, and then go back and finish the first triangle. So we found angle A. Now we can easily find angle C. I'm going to take this away so it's less distracting. And this is angle C1, which we already know two of the three angles, so that's going to be easy. 180 minus 61 minus 106.9. And again, if I had falsely assumed that this creates a second triangle, this is where I would figure it out because the angle would be too big. Angle C is 12.1 degrees. Sorry, C1. So 12.1 degrees. And then finally, I will go in and find side C1. This is where I can use law of sines. I have sine of C1 over little c1 equals sine of, it's always better to use the given pieces, so b1 over little b1. Fill in your info. We have sine of 12.1 over, that's unknown, so little c1, equals sine of b1 is 61 degrees, over little b1 is 32. Cross multiply. Again, I'll skip a little bit of work here and just explain what's going on. 32 times sine of 12.1. And then these two will multiply as well, the sine of 61 times c1, and then we'll end up dividing both sides by that sine of 61. So that's going to end up on the bottom of our fraction. And then calculator to get my final answer. And that rounds to 7.7 if we go out to the tens place. So lastly, my side C1 is 7.7. So there is one of the two triangles fully solved for. Now let's go back and find the rest of the first triangle that I made. So the process is going to look exactly the same. The numbers will just turn out differently. So first we find angle C. Once again, we know two of the three angles, so this part's quite easy. 180 minus 61 minus 73.1. $45.9 degrees. So that's my angle C, 45.9. And then law of sines again to find side C. So we have sine of C over C equals, again, use the givens, which are the B's, sine of B over B. And then we have sine of C is 45.9 over C equals sine of big B is 61 over little b is 32. Cross multiply. Solving for C, we will have 32 sine of 45.9 over sine of 61. And then using our calculator to get the C value. C is approximately 26.3 in length. And there we have it. Those are our completed triangles. Now, a couple things. Again, we only at the time knew that A was bigger than B, so that's where we can make this second scenario, that A is either acute or obtuse. Second, the value of A directly affects the value of C, because obviously with the 180, C can only be a certain number once we know two of those three angles. So it did turn out that A is the largest angle in the triangle. So it very well could be an obtuse angle. Once again, we don't know which case is the correct one, but we do know that given these measurements, we could actually make two triangles out of it instead of just one. And that all comes back to the fact that we are using law of sines, and therefore on the angle measurements, so let me go back to when I found A, we're using inverse sine to find A. An inverse sine cannot give us a number larger than 90 because that's the top of its range. If it can't give a number larger than 90, then the largest angle it will give us is a right angle. It will not give us any obtuse. So that's why we have to go look through that for ourselves. So once again, that demonstrates the whole phenomenon that happens here with the angle side-side ambiguity case. I hope this video helped and kind of cleared up any confusion you might have. I am going to make a second video over this using a geometry explanation. I personally prefer the Precal explanation. I think it connects on many more levels than the geometry does. But if you think that might be something that makes more sense to you, go check out that video instead. Otherwise, I hope you guys have an awesome day. Bye.